There we go. Okay. So let's talk a little bit about each of these different types of analysis, just so we have a general understanding of what they are, and then move into specific techniques that you can use. So the first one we're going to look at is univariate analysis. Univariate is pretty much a fancy way of saying that you're analyzing a single variable. So it can be used to understand distributions and to learn more specific things about the data itself so that you understand kind of the structure of your data a little bit better. And some easy ways to do this are to generate some statistics. Normally, if you use this describe function, you'll get a few different things. You'll get a count, which is basically just the number of rows in most cases. You'll get the mean, and this is all for numeric variables, by the way, because of course you can't calculate a mean for a categorical one, or at least you shouldn't be able to. And then you have your standard deviation, the smallest value, the largest value all the way down here, and then your percentiles. And that's useful for understanding if you have any outliers, which can also be done by using a box plot or something like that. But again, if you just use this .describe on the data frame itself, it'll actually run all those statistics for all of your numeric columns. Right. Got it out in the end. Okay. And the mode is a useful one specifically for your categorical variables. So for instance, whether or not they have a verified host identity, the neighborhood group, this is all using the Airbnb data that we looked at last time, by the way. So this is more like which neighborhood group is the particular listing occurring in. And it'll also show you the mode for your numeric variables too, which can be helpful in some cases. You may also wish to know within a single variable some distributions as to the possible values, especially if it is a categorical variable. That being, say, the DF neighborhood group, and seeing how many of these value count, or seeing how many instances of each of these subtypes are occurring. Now, there's something important to note about this data. There is a typo. Instead of Brooklyn, it's Brooklyn, which kind of just goes to show you that whenever you're going through EDA, or really any of the processes as you go forward, you may notice that your data could be more clean, and that you just need to go back and reiterate on the data cleaning process that you did before you started analysis. It really just goes to show you that all of this really is recursive and iterative. And yeah, that's pretty much it. Now you can also show the percentage of these categories too, which can be helpful. And if you're wanting to do some plotting, for example, if you want to see if your numeric variables are normally distributed, because some of the tests that we'll get to require that, then you can just use the data frame and then use the histogram function, which will generate these histograms for all of your numeric variables. Here we see that they're pretty much just flat across the board, which means they are not normally distributed. And that is good to know because some of the techniques we're going to talk about require your data to be normally distributed. This one is strange, mostly because almost all the values are occurring here at the very small, or the smallest possible value. And then there are some going all the way up to 300. But They're rare. This is by far the most common. Now here you can also make box plots for all of your applicable ones. And whenever you see PLT, we are referring to the Matplotlib package, which is basically a data visualization package. If you want to use that, then you can just use import matplotlib pyplot and then rename it to PLT. Basically, this will allow you to show your visualizations, to add titles, label titles, and adjust colors, the positioning of these, all sorts of different things. So Matplotlib is a really easy way to add extra information to your visualizations. Now, you can do more advanced things whenever you are working in Seaboard, but Matplotlib will take care of most of the visualizations that you need to do, which is why we're focusing on it for right now. And here, this is just using it for a bar chart, which can also be important, because here we can see how overrepresented Manhattan and Brooklyn are compared to these other possible neighborhood groups. Almost all the listings are occurring in these two neighborhood groups. And that is actually important to know whenever we get into the machine learning side of things, but we're not focusing too much on that right now, so I'll leave that be. Now, the second thing that we're getting into is called bivariate analysis. As the name kind of implies, you're looking at how two different variables relate to one another. So basically, you could look at the price and compare it to the neighborhood group and say, okay, how does the neighborhood group impact the price of the Airbnb listing? And this can be helpful for determining what you want to analyze further, and even for a simple analysis if somebody's just looking to see that. And there are stats methods and visualizations, but we should always have a good idea as to what the data is itself before we get too far into things. And one thing you can do is produce tables that basically show both of your variables together. So what this is doing is calculating the count, mean, standard deviation, etc. of the price for each neighborhood group. So we see here that there are about 2,600 listings in the Bronx. Their mean price is 628 or so. That's a standard deviation, etc. And we have that produced for all of our possible neighborhood groups. And this can be useful for understanding differences within the groups and seeing those different distributions. So this is seeing which neighborhood group has which room type. And this is just going off of the counts value. So here, we had a couple different room types. You could have an entire home, a hotel, private room, shared room, and different neighborhood groups. And we see that the Bronx had, by and large, homes and apartments, and then private rooms, those being at about 1,000 and 1,500 respectively. We see Brooklyn has a massive spike, as does Manhattan, for the number of rooms and apartments, but still they don't have very many hotel rooms or shared rooms, especially compared to those more common categories. So really, home and apartment and private room are by far the most common, regardless of the neighborhood group. But this does allow us to see that they do differ between the groups, at least slightly. Now, there are, as I implied, a pretty good number of techniques that can be used in bivariate analysis. And here we're going to go over some fairly standard statistical methods, along with visualizations that you might use to better understand your data. So, starting with the statistical methods, we have a few to cover, that being t-test, ANOVA, chi-squared, and correlation. And I'll explain why all these are used as we go along. And I'm not going to go too deep into code, but it is present. And I will be sharing the code afterwards if anybody wants to dig deeper into that. So here, a t-test is basically used to compare the means of two groups and see if the difference between those means is significant. So let's say we go back up here and we see that the mean price in the Bronx is about 629, whereas the mean price in Brooklyn is about 626. So we're trying to find out if that difference is actually significant. Basically, how the t-test works is it'll compare those two data sets and those means and see the percent chance that the difference happened by pure coincidence. So here, basically, I'm filtering down to the neighborhood groups and down to Staten Island and then I'm initiating the t-test itself. And what this does is show us a p-value. The p-value is one of the most important statistics that you can see in any of the models we're going to talk about today. So it's important that you understand this. The p-value is basically the probability that your result occurred by chance. So here, we're comparing these two means, and this p-value is showing us that there is about a 72% chance that the difference in these two means occurred at random, which isn't all that impressive, right? Because if it has that high a probability of just happening by chance, then is it really that significant of a difference? Probably not, because more than likely it just happened for no real reason. Typically, what we look for in a p-value is a threshold of 5%. And sometimes we even go down to 1%. Obviously, this being 72%, that's way above our threshold. And we would not consider the difference between the mean prices in the Bronx and Staten Island to be significant. So if you just wanted to compare that, a t-test would be good for you. And now, ANOVA can be used to compare the means of 3 or more groups, whereas a t-test will only compare 2 things. Now, a little bit of a misconception is that ANOVA can be used on multiple different variables, which isn't entirely true. It's more like you're comparing the means within a single group. So here, you only have 2 variables. Your variables being which neighborhood group is it in and your price. And we're just looking at the price mean for all the neighborhood groups and seeing if the difference between them is significant. So we're still working within that single variable being the neighborhood group. We're not branching out of it, even though we have multiple neighborhood groups. Now here, whenever I run the one-way ANOVA and I compare Brooklyn, Manhattan, Queens, Bronx, and Staten Island, our p-value does drop down to about 18%, but that's still not at our threshold. So we can't say for certain that there is a substantial difference between these prices. And now, a chi-squared test is a bit different. If we look at what we've been comparing with ANOVA and the t-test, we're looking at means, which means that we are looking only at the differences in quantitative or numeric variables. However, a chi-square test can look at the relationships between categorical variables. For instance, in this case, we can look at the relationship between the neighborhood group and the type of rooms that occur in those neighborhood groups. So, for instance, we can look and see like how many of these whole houses or apartments are occurring, and then compare that between Staten Island and Brooklyn. And whenever we generate this, we compare all the neighborhood groups to all the room types, we actually get a p-value of 0. So there is a significant difference in what is being offered between these neighborhood groups and the type of rooms that they have. What exactly that difference is would need to be seen by looking at the data itself, but this chi-square test can tell you definitively that there is a difference. So if you look at the data and suspect that there's a difference, you can run a chi-square test and see if there is. Likewise, if you're not sure if there is a difference or not, you can run this to validate that and then look back at your data to see what that difference is. Now, correlation analysis is kind of getting into visualization simply because it's easiest to view correlation as a correlation matrix. And to make a correlation matrix, the best way is to use the Seaborn package. So what you can do is basically store your correlations and then create a heat map that uses that correlation matrix. And like with Matplotlib, you can change your colors, you can change whether or not you want to have these labels, all that kind of stuff. So here, I just looked at the correlations between everything, but at each of these intersections, it's only comparing 2 variables, so it is still bivariate. Now, you of course want to be careful whenever you look at these ones that occur at a correlation of 1, because oftentimes that's going to be comparing the variable to itself. So here we see like calculated host listings count has a perfect correlation with calculated host listings count. Of course, it's going to be completely correlated. It's literally the same values. But what gets more interesting is if you see something like this. Your service fee and your price is at a correlation of 1. But let's take a step back and figure out what that correlation actually means. In each of these squares, we have something called the correlation coefficient, which is sometimes called the R-squared. And this value will show you how well one of these variables can predict a change in the other one. It's almost like a percent difference in a way. Basically, you want to think of it like this. If the absolute value of this correlation coefficient is close to 1, then it has a strong predictive relationship. And then, if it is positive, that means that the values will increase together. So here we see that as the price increases, the service fee will also increase. And it has a perfect relationship. And if it is negative, then the values will shrink, or one of the values will shrink as the other one increases. So here we see like it's not a strong correlation, so it would not be useful to look at this. But you can see that maybe the construction year has a negative impact on the service fee, or vice versa. But understanding those correlation coefficients is important because it kind of shows you where relationships in your data exist and can help you to see what you might want to analyze further. And now some common visualizations for bivariate analysis are scatter plots. And this data is not really good for making scatter plots, but basically you can think of it as like a ton of random dots along there. And if they cluster together and they form a nice line, then you can say, okay, they probably have a strong relationship. And then of course, if it's going like this, it's a positive one. If it's going down, it's a negative one. But you can also say it may not have that strong relationship anyway. And now you can also, of course, make bar charts. And here we're seeing pretty much the mean price for each of these different neighborhood groups. And as we look at this, we see that there's really not much of a difference at all, which we also validated with one of our statistical tests earlier. So that's pretty self-explanatory. Now, the more complicated of the three forms of analysis that we've talked about is multivariate analysis. Multivariate analysis, as you might be able to deduce, is used to examine the relationships between 3 or more variables. And that complicates things because with a bivariate analysis, you really only have a few different possibilities as to like where your categorical variables are and where your quantitative variables are, and you pretty much know what you want out of that relationship anyway. But with multivariate, you may not even know what you want, and there are a ton of different configurations of variable types. And so multivariate analysis can be really helpful to limit the scope of your analysis, both in terms of what you want to analyze and the variables that you use in your analysis. And I'll explain a little bit more about the difference between those two things after I introduce the two multivariate analysis techniques. So multivariate is best split into two camps, those being dependence techniques and interdependence techniques. A dependence technique is the easier of the two to understand by far. The dependence technique just looks at how a dependent variable is predicted by one or more independent variables. So say we can look at the price and see how it's affected by neighborhood group and the service fee. Whereas before, if we're looking at a simple bivariate analysis, we'd have to choose one of those two predictors whenever we're looking at the price. And there are a few different dependence techniques, but before we get into those, I just want to talk a bit about interdependence techniques. So interdependence is strange, but it is important because it helps us to see things in the data that we might not have thought about. So interdependence doesn't directly look at dependent and independent variables, but it's used to understand relationships in the data. It helps find patterns and structures and things that you might not be able to find without machine-assisted analysis. They pretty much just find relationships in your data without specifying what you're actually looking for, which is really helpful in a couple different contexts. And now, a quick note on linear and logistic regression. These are really some of the most common bivariate and multivariate analyses that you will use. But we're not talking about them today because we're going to be talking about it in 2 weeks. separately from anything else. So linear and logistic regressions are kind of at the intersection between exploratory data analysis and machine learning, and are used in a lot of different contexts, which is why we're breaking it apart from everything else. But I'll get back to them and talk about where they fit into these analyses as we go forward too. So as we go back to these dependence techniques, we have several different techniques that we can use. And as I alluded to earlier, it depends a lot on the variables that you have. So if we look at conjoint analysis, we can see how a dependent variable is affected by categorical variables. However, it does not matter what type of variable the dependent is. So I could say, look at the neighborhood group and the host listing verification and predict the price, or I could predict some other categorical variable. Right, so conjoint analysis allows us to work on both of those fronts. And multiple discriminant analysis helps us to see how a categorical dependent variable is affected by multiple independent numeric variables. So say we want to predict where a listing is located based on the price and the service fee, and maybe even the construction year. We could do that using multiple discriminant analysis. Of course, that assumes that it can make those predictions accurately, but this tool can be used to see if it's even possible to do that. And going into the linear probability model, we can see how the categorical dependent is affected by multiple independent variables, but it doesn't matter if those inputs are categorical or if they are numeric, right? It really doesn't matter what we give it. It'll just be able to predict the value of a category. And now, MANOVA is really similar to the ANOVA that we talked about earlier. It just allows us to work with more variables. Basically, it allows us to look at how these numeric dependent variables are affected by categorical independent ones. So again, looking back at, say, the whether or not the host is verified and the neighborhood group, we can predict the price and we could predict the service fee, because this does say you can predict several numeric dependent variables, which makes it distinct from what we talked about earlier. Because a lot of these are only saying you can predict a dependent, but starting at MANOVA, you can predict multiple dependents, which is really helpful because it allows you to analyze how several different things are related to each other, rather than just looking at how this bunch relates to this one thing. You can just look at how this bunch relates to all of this bunch of things. And canonical correlation analysis is in a way similar to MANOVA in that it allows you to look at all these different things together, but it just kind of switches the things a little bit. So this is looking only at numeric variables. This data isn't great for canonical correlation analysis because we don't have that many numeric variables, but you might be able to say, look at how the price and the service fee are affected by the construction year and the total number of listings that particular, or the number of visits that particular location has had. You could do that. You could see the relationship between those two groups. Now, I haven't provided code for these because really it doesn't come up that often. But they are helpful to know, at least conceptually, because you might come across a situation where you see, oh, I need to know a little bit more about this, or I need to know a little bit more about this particular situation in my data. Even if it doesn't apply all the time, it's helpful to know because it applies some of the time. Right? So you can always say, okay, I know I need to know how this particular thing is affected by several variables, and I know I can use a conjoint analysis to see how that looks. Now, an important note about these dependence techniques is that both linear and logistic regression are dependence techniques. So again, they can predict a dependence using multiple independents. But what do they actually do? A linear regression can be used to predict the value of a numeric variable, whereas logistic regression can predict a categorical variable, right? And the output for that categorical does not necessarily have to be binary either. So you can say, instead of predicting whether or not a location is in the Bronx, you can say, I want to predict if this location is in the Bronx or in Staten Island or anywhere else, right? You can have multiple categories that you try to use logistic regression to predict all at once, so long as they are within the same variable, if that makes sense. And linear regression is not that flexible. It's pretty much just predict a numeric variable like the price based on all these different inputs. Now, linear and logistic regression, if I remember correctly, can work with multiple different data types, but that'll be worth looking into. And now, interdependent techniques are very flexible because, as I alluded to earlier, they don't examine dependence and independence directly. They're really used to find relationships. So factor analysis is an example of this. Factor analysis examines the relationship between your data and groups together variables that have high correlations. But why would that be beneficial? It's beneficial because it helps you get rid of variables that you do not need for your analysis. And really all of these things do, but factor analysis especially does. So think of it like this. In this data, we have both the neighborhood group and the neighborhood. Okay? Those two things are going to be pretty highly correlated to one another. And it may be that there's really not much of a difference between those neighborhood groups in the first place. So if we include both a neighborhood group and a neighborhood, it's going to add extra noise to our data and alter the accuracy of the models that we run later. So basically what you're saying is like, hey, I have this predictor, and they're basically the same, and model, try to work with it. But that does two things. One, it can impact your model's accuracy because it's working with a lot of extra information that it doesn't need. And it impacts the computational costs of running your models. So by removing that excess variable or excess variables, you are reducing down to a much more manageable variable set. And that helps your models run more efficiently and potentially more accurately. So by looking at any of these techniques and saying, okay, so these two things are highly correlated, so we might be able to get rid of one of them, or saying, okay, this thing really doesn't have much of an impact at all, so we can get rid of it. You are filtering down to the most relevant predictors. And now you are able to use those in your models, and that'll make everything a lot easier to run and potentially more accurate. And that's really a pretty big reason for doing EDA, aside from just understanding the data and generating some basic statistics that people might want to see. Like, yeah, it is cool to see the mean price of all these different neighborhood groups, but that's a pretty basic analysis. But as we go through the EDA process, we can see what actually is relevant and figure out more advanced questions we can ask and figure out the best way to approach those questions. Again, by filtering down your variables, right? Because again, if you have too many variables, that makes it slow and that can impact your accuracy. Now, that's just talking about factor analysis. Cluster analysis is a bit different. And basically what that does is allow you to group your data together in different ways. So like, this isn't a perfect example because we're looking at interdependence, but let's say that you wanted to group the price into low, medium, and high. You can do cluster analysis to basically break it down and be able to apply labels to your data that way. And this is still useful because cluster analysis can be used to say, understand what impacts the neighborhood group that a listing is in. Again, it's not perfect because cluster analysis really doesn't come up all that often, so I'm not an expert with it, especially not for interdependence techniques. But really think of it as a way of grouping your data into smaller sets that you can look at and understand much more intuitively than you would be able to otherwise. Right. And one thing to note about visualization in Python is that it can get a lot more advanced than what I'm doing in any of these files. Most of what I'm doing in the files that I send out and what I show on screen are basic approaches to any of the things that we're talking about. But especially for visualization, you can get a lot more advanced. So instead of, say, just generating this bar chart, I can apply all my labels. I can give it a title. I can change the color of this. I can change the color of each individual one. I can export the image, and I can even change the size of the image itself. So if I know I need it to be a certain size, because I'm giving a presentation and it needs to be large enough so that it would be visible in the presentation, I can specify the figure size, which is just the dimensions of the image. Now, I'm not really doing that too much here because it's a little bit outside of the scope of this, but visualization can get a lot more advanced than what I'm talking about here, especially if you get deep into Seaborn. One thing you may have noticed is that I don't really use any pie charts. even when it seems to be relevant. Like if we come up here. Here we're looking at the percent of all the listings that occur in a given neighborhood group. So in Manhattan, we have about 45% of all the listings occurring there. Whereas in Brooklyn, we have about 40% of all the listings occurring there. And going down and down and down. The reason why we don't really use pie charts too terribly often is that it can be difficult to compare any of the slices directly, unless the slices are either significantly different in size, or if you have a very small number of slices. Which is why, especially in this instance, where like these two are almost the same and these are almost the same, it would be a little difficult to tell exactly what's going on in a pie chart without adding extra labels, which makes it look messy, that kind of thing. So bar charts are often used in place of pie charts, even when you're traditionally told that a pie chart might be the best option. This isn't always true for a business intelligence position, because in there you're working with Power BI and stuff like that, and it's a little bit more flexible. But in general, for data science and for data analysis, we prefer to use bar charts over pie charts. Right. And there are a lot of different types of charts, way more than you're usually taught. But really the main ones are going to be your box plots and your bar charts, along with line graphs and things like that. Pretty much what you've always heard of going through school. So there is not too much more to talk about with EDA and visualization today, mostly because, like I alluded to earlier, EDA is very flexible and there are a lot of different approaches to it. So if we were to try to dive deep into it, we would probably need the entire semester just to do that. But I do hope that this at least has given you a bit of an overview as to the different techniques and the different types of EDA that can be performed. But let me look at our time. It looks like we got about 8 minutes for questions and things. So why don't we just go from there, see if y'all have any questions or anything about what I've done. Feel free to ask. Okay, so it doesn't sound like there are any questions about this exploratory data analysis or visualization or anything. So again, if there are no questions, that's fine. We will be talking about linear and logistic regression in 2 weeks, which again gets back to our bivariate and multivariate analysis. And in truth, those forms of analysis can replace quite a few of these, but we work with what we have. And sometimes it is better to use some of these alternative techniques. And again, linear and logistic regression being split off for reasons. But yeah, feel free to join us for that. And next week at the same time as this meeting was, we are going to have some guest speakers come in from Enable. Yes, Lucas, this was recorded, and I will be sending a link to the data and to the notebook. It'll be on our website, and this audio and video will be uploaded to our YouTube page. And we have had some issues tonight with audio. So if there's no sound in that video, I'll just record myself lecturing over it and then upload that instead. But either way, there will be a video for this. So and the data and the code itself. But yeah, that pretty much covers what I have to talk about today. Like I said, there will be guest speakers coming in from Enable this times next week. And in 2 weeks, we will have our next lesson in the Python series. All right. So any more questions before we head off, or? All right, awesome. And today's the last day to pay your dues. If you haven't, remember, you do need to pay your dues to attend any future events. But with that in mind, take care, y'all. Have a good night.
Oh, Max, share it here.
Yeah, I know you're saying behind Shrub.
Yeah, okay.
But yeah, have a good night, the rest of y'all.